So we'll now start the student interaction. We'll come one by one. All right. So YCC College, now we are going to start interaction with the students. So very warm welcome to all the students. I'm very happy to see all of you here. Now I would like to have questions and discussion with the students in the presence of the faculty. So please come forward, students, and ask and talk to us.
Hello, sir.
Yes, hello. Introduce yourself and welcome.
Good afternoon, sir. I am Bhuvnesh Mahajan from YCC.
Okay. Welcome. What's your name? Swapnil?
Sir, my name is Bhuvnesh Mahajan.
Bhuvanesh. Okay. Welcome, Bhuvanesh.
Sir, could you explain differentiation in time domain? Excuse me, sir. Sir, Fourier transform of differentiation in time domain.
Okay. So, Fourier transform behavior of differentiation in time. All right. Now see. Now you see, let's take a simple sinusoid, a sine wave. So let xt be a pure sine wave. Let's say a cos omega t plus phi. What happens when you differentiate this? You get minus a omega sine omega t plus phi. Now how do you write this? You write this as, and if you want to write it in terms of the original wave, what are you saying? It's a omega cos omega t plus phi plus pi by 2. Is that correct? That means, what have you done to the sine wave now? You have done two things. The amplitude has changed. And how has it changed? The amplitude has got multiplied by the frequency value, the angular frequency value. And the phase has also changed. Both the amplitude and the phase change. Now go to the Fourier transform. What do we do in the Fourier transform? In the Fourier transform, you are in fact thinking of xt as comprising of many of these sine waves. So each of the sine waves undergoes this kind of a change of amplitude and change of phase. So on the frequency axis, angular frequency axis, how does the magnitude change? The magnitude response of this differentiator, the magnitude changes according to the frequency itself. So the magnitude response is mod omega. And how does the phase change? For positive frequencies, it changes adding a positive angle of pi by 2. And for negative frequencies, it adds an angle of minus pi by 2. So for positive frequencies, this is 0. So for positive frequencies, there is a pi by 2 phase change. For negative frequencies, there is a minus pi by 2 phase change. Is that right? This is because each sinusoid actually comprises of one positive frequency and one negative frequency component, and together they make up the sinusoid. So the positive frequency is changed by pi by 2, the negative frequency by the negative of that, minus pi by 2. And I showed you what happens with one sine wave. So this happens to all the sine waves in the original waveform. So that is the magnitude and phase response of a differentiator. Is that clear, Bhuvanesh?
Yes, sir.
Very good. So can we have some more questions from your team?
Hello, sir.
Hello.
Hello, sir. My name is Atul Chau.
Yes, Atul, welcome. Good afternoon.
Hello. Sir, can you Sir, can you explain the duality property of continuous time Fourier transform?
Sure, we talk about the duality property, yes. You see, what is the duality property? So, duality property is one of the privileges of an electrical engineer. I keep saying electrical engineers are very privileged because they learn one and get one free. Okay? So, you learn one Fourier transform and you get one Fourier transform free. So, why does this happen? This happens because the Fourier transform and the inverse Fourier transform have very similar forms. So, the Fourier transform looks like this. The inverse Fourier transform looks like this. Now, look at these two expressions, they are very similar. In fact, in this expression, if we exchange the role of t and f, so we write f in place of t, and we write t in place of f. And these two of course remain the same because it is a product of the two quantities. What happens then? X of minus t can be obtained simply by negating this argument here, isn't it? So, x of minus t becomes the Fourier transform of capital X of f. Do you see that? So, if x t has the Fourier transform capital X of f, then x of minus t is the Fourier transform of capital X of, or rather x of minus f, you know. So, you write x of minus f here. So, you write x of minus t first, as I have done here, and you can put the minus sign there and then interchange f and t. So, let us summarize this. What I am saying here is that if x t has the Fourier transform capital X of f, then capital X of t has the Fourier transform small x of minus f. Now, what is the application of this? For example, you know that if I have a square wave, or rather square pulse, a rectangular pulse if you like, x of t, its Fourier transform is of the form sinc, so sin af by bf, isn't it? That immediately tells you that if I have a sinc function in time, its Fourier transform would be a rectangular function in frequency. So, if you learn one Fourier transform, you get one Fourier transform free. That is what duality tells you. Is that clear, Atul?
Yes, sir. Yes, sir.
Okay, next question.
Excuse me, sir. There is a doubt in that duality. So, what is the difference between small x of t and capital X of t?
Okay. So, small x of t means you are pretending that the Fourier transform is a function of time. So, you know, you write the same shape, write the same function, but write time on the independent variable axis. So, whatever Fourier transform you got was a function of frequency, but now frequency also goes from minus to plus infinity. So you can play, you can interchange the role of frequency and time. Now you can call the independent variable time there. So you take the same function as the Fourier transform, but make that a function of time, not of frequency. That is what capital X of t means. Is that clear?
Can you repeat?
For example, let me tell you an example. Now you take the sinc function, you take the sinc function. So let's take the sinc function. How does the sinc function look? It looks like this. The sin x by x kind of, sin x by x kind of pattern. Now sinc function in time gives you this kind of a Fourier transform. So here the Fourier transform is obviously a function of frequency. Now you can also take a rectangular pulse in time that would look like this Fourier transform, and it's the Fourier transform of this rectangular pulse is going to be a sinc function in frequency. So the role of small x, and so small x refers to the function, original function, capital X is its Fourier transform. But now you can interchange the roles. You can make the Fourier transform a function of, you could take the same shape as the Fourier transform and construct a time function like that. And then we are saying the frequency, the Fourier transform of that new function looks like the original function, but with time reversal. Is that clear?
Thank you, sir.
Okay, we'll take. Okay, let's now take any other questions from YCC. So we'll listen to the. All right. So we'll listen.
No, sir. Thank you, sir.
Okay, so you must continue. Don't go away. You must listen to the questions from the other centers. Now let's have a question from Rice. I think we had some questions from Raisoni College, isn't it? So let's go to Raisoni College. We had several students there. Let's have some questions from the students there. So very good afternoon to you, Raisoni College. Let me have your questions. Yes, a very good afternoon.
Hello.
Introduce yourself and ask your question.
Good afternoon, sir. So it's Piyush Shemde from GH Raisoni.
Yes, Piyush, good afternoon and welcome. Tell us what your question is.
So my name is Piyush Shemde from GH Raisoni, Electronics third year. So my question is, sir, we had registered the enrollment form, but we are getting query that it is showing it has not been done successfully. And now it is being closed. So what to do now?
So we'll open the registration. I think it was open only till 26th or something. We'll extend the registration date. I'll get it done right after this meeting. So you should check around 6 o'clock
sir.
or something like that. It should be done.
Okay, sir.
Okay.
Okay, very good. Now we'll have some more questions from Raisoni College. So a very warm welcome to all of you. I can see several students have come to interact with us.
Good afternoon, sir. My name is Samreen Nas. I have one question. What is the discrete time Fourier transform of a raised to n u of n?
Okay. So very good. So now the question is, what is the discrete time Fourier transform of a raised to the power of n u of n? See, first, I don't know whether you have reached the, but anyway, let me answer the question. Yeah, I think we have not started talking about that in the course, but still I'll answer the question. Now, how do you calculate the discrete time Fourier transform? You take the dot product of this with a rotating complex number sampled. So, in general, suppose this is x of n, then how do you take the discrete time Fourier transform? Xn, take the inner product with a rotating complex number, rotating with angular frequency omega and sampled at the integers. Let us evaluate this for the particular sequence which you have given. Now, this is a very easy sequence to evaluate provided mod A is less than 1. If mod A is not less than 1, this cannot be evaluated. So, provided mod A is less than 1, this is a geometric series, it's a geometric progression. So, it is 1 plus a e raised to the power minus j omega plus a e raised to the power minus j omega squared and so on, which was very easy to evaluate. It is 1 divided by 1 minus a e raised to the power minus j omega. So, this is the discrete time Fourier transform of the sequence which you have given. Is that clear?
Yes, sir.
Next question.
Thank you, sir.
Good afternoon, sir. My name is Samiksha Lohukare.
Okay, yes,
My
Samiksha.
question
Yes.
is e to the power minus a mod of n, signum of n.
Okay.
Discrete time Fourier transform of e to the power minus a mod of n, signum of n.
Okay. So, the discrete time Fourier transform of e raised to the power minus a mod of n times signum of n. Now, what is signum of n? Signum of n is positive or 1 for n greater than or equal to 0. And some, of course, there is a little bit of ambiguity at 0. So, you can, I'll leave it to you to complete the evaluation, but this is very easy to evaluate. This is again two geometric series. How will you find its discrete time Fourier transform? It is summation n going from minus to plus infinity, e raised to the power minus a mod n signum n e raised to the power minus j omega n. So, you need to split it into two parts. You need to take the positive n first and then the negative n. Is that right? Now, both of these are two, each of them is a geometric progression. So, you can evaluate just as I did for the earlier example, you can evaluate the sum. So, is that clear?
Hello. Good afternoon, sir.
Good afternoon.
Hello. Good afternoon, sir. My
Yes.
name is Shubham Kulkarni.
Yes, Shubham.
I am having one question.
Yes, go on.
Sir, we have registered. We had a IIT Bombay site, but they are saying that users are not registered. What to do now?
No, I didn't. What you've already registered, but as in when you're trying to log in, this is coming or
And one.
no? Yeah, continue.
नहीं एक्चुअली कैसे है कि रजिस्टर हो चुका है IIT बॉम्बे साइट पर.
Mm-hmm.
हेलो.
Yes.
I had registered in IIT Bombay,
Okay.
but they are saying that user are not registered. What
so,
to do?
So when you go to itbombay.x.in, okay, you need to click login on the top right. So when you click login, you need to enter your username and password. After that, what is happening?
Yes.
So after you type your username and password, what is happening?
It is logging. It got login.
Okay.
Login is happening.
Okay.
But after logging, after login, they are saying that
They're saying.
course is not displaying.
Okay, so course you need to register for the course.
Course is
So-
not displaying.
So which means you have not registered for the course. No, so you need to go to this. There'll be a search option at the end, somewhere at the top, and so let me open my window and yeah. So there should be a search window on top. No, I'm not sharing. I don't want to share. So let me just-
Now enrollment is closed. They are saying that.
So someone else already asked that question. So what we're going to do is we'll reopen the enrollment. So it should be done by around 6 o'clock or 7 o'clock today.
Okay.
Can share it? Want to share?
Okay. And one more question.
Yeah.
Many users having question that they have invalid username. What to do for that?
Invalid username. So either they have not entered the username that they used during creation of the account, or somebody else has already taken their username. So you'll have to choose some other username while registering.
Okay. Thank you. Thank you.
So the username is supposed to be unique. So if someone else has taken a username, you cannot use the same one. So just like your email ID.
Yes, ma'am. Sir, you have already earlier said that for signum of n, it is for greater than 0, greater than equals to 0, it is 1, and minus 1 for less than 0 and less than 0. Then what about n equals to 0?
So that's a good question. See, for continuous time, actually the point 0 doesn't matter so much. For discrete time, this is a bit of ambiguity. Some people like to say signum of n is equal to 0 at n equal to 0. So some people like to define signum n like that to make it symmetric. Some people like to give it the value 1 at n equal to 0. So, it depends on how you define signum. There is a bit of ambiguity in the definition of signum for discrete sequences. But you must write down what definition you have used and then work according to that. Is that all right? So now let me have questions.
Yes, sir, thank you.
Yeah.
Sir, I have
Yes. Are there any other students who have
I have
questions?
one suggestion.
Yes.
Yes, sir, I understood.
Yes. Yeah, go on.
Sir, I have one suggestion that please provide solution to quiz.
So quiz was provided.
The quiz solutions have been provided.
So quiz 1 solution is out actually. So quiz 2 solution will be out after the deadline. Quiz 1 solution should be out.
Yes, sir.
So quiz 1 and the solution should be out. We'll just check.
Should be out. I'll just check 1 second. Give me a minute. Oh. Okay, 1 second. Okay, so I'm not able to see it. Okay, I'll have a look. I'll double check on that, but it should be out.
Hello, I'm Rohit Prakash Podwal from GH Raisoni College of Engineering.
Okay.
Yes.
I have a question. What are the advanced topic we should study for this subject?
Advanced topic.
1 minute.
What are the advanced topic we should study for this subject?
What are the advanced topics? So what are the, see so far what have you studied in the subject?
Fourier, like how to calculate Fourier transform of various signals,
Okay,
and various types of signal system, and how to calculate Fourier transform of various types of like continuous signals and discrete signals.
okay.
So what advanced topics we could study for this subject?
So now advanced topics, you're going to study sampling. So see, so far you're treating continuous time systems and discrete time systems separately, but now you're going to bring them together. How can you use discrete time system principles? Or how can you use discrete time system concepts to understand continuous systems? That can be done through sampling. So sampling, reconstruction, and more general transforms like the Laplace transform, the Z transform. These are some of the advanced topics you are going to study. Is that right? Piyush, no, what's your name?
Yes, sir.
Okay, so
And just to answer the other question, so the solutions have been released. What you need
Thank
to
you,
do
sir.
is, yeah, so what you need to do is you need to go to the quiz 1, which is already out, and just click show answer. Let me see if I
Okay, thank you very much, sir.
yeah.
so Ashwit is telling you how to see the quiz answers. Some of you have asked, so he's telling you how to see the quiz answers.
Just click show answer for the question. You'll be able to see the complete
Would
solution.
you like to share the?
That's fine. That'll take time.
Okay.
Should we go to the next college?
All right. So any other questions from Raisoni College?
Okay, sir.
All right. So we'll now go to Banari Amman Institute of Technology. So very good afternoon to all of you. I can see there are several students waiting there.
Good afternoon, sir.
Good afternoon.
Good afternoon.
Yeah, good afternoon. Go on.
Good evening, sir.
Good evening.
I'm Subramanian Krishnan from BIT.
Yes. Welcome.
What is the real application of using RAM signal in real time in real life?
What is the real application? Can you repeat of using which signal? The ramp signal.
RAM signal.
The ramp signal. See, let me give you an example. What will happen if you give a DC to a capacitor? As if you give if you give a constant current to a capacitor, what will happen? The voltage will start growing like a ramp. Is it not? So ramp signal occurs in practice when there is an integrator operating on a constant. Right? When you have an integrator operating on a constant, you get a ramp. That is one of the practical situations in which you get a ramp. Now, the ramp signal, there are other situations in which you use a ramp. For example, if you look at the cathode ray oscilloscope, you need a ramp signal so that you can move across the screen. If you want to move across the horizontal screen, you use a ramp signal input to the screen. Okay? So there are many situations in which a ramp signal is used. Is that clear?
Yes, sir.
Yeah. So do we have other questions? Yes.
Sir, I am Raghavi from BIT.
Yes, welcome.
Hello.
Yes.
Sir, why we represent continuous time signal as x of t and discrete time signal as x of n?
Okay. So it is just a convention. There is not, you don't have to do that, but it's a convention that small t is often used to denote a continuous independent variable time, and n, p, q, these are some letters which are used to denote integers. It's a convention. There is nothing special about those letters. There has been a convention in the literature, right?
Thank you, sir. Good evening, sir. I'm Sri Harni from VIT.
Yes. Yes, Sriyarni, go on.
Yeah, for a signal, it should be non-causal. So the future value should not be present in the signal. But in the deterministic signal, we are predicting the future signal. So what is the use of preferring the deterministic signal?
So, see, a signal is not causal or non-causal. It's a system which is causal or non-causal. Okay? A system is said to be non-causal if it does not obey the cause and effect relationship. That means, if a signal, if there are two identical inputs up to a point in time, and if the system produces different outputs for such identical inputs up to a point in time, and that can only happen because the inputs are different in beyond that point in time, isn't it? So, if a system responds to inputs which have come beyond that point in time, we say the system is non-causal. Now, it is a system which is causal or non-causal. Signals are not causal or non-causal. Is that clear?
Thank you, sir. Good evening, sir.
Good evening.
I'm Hemlata from VIT.
Yes, Hemlata. Yes, go on. Welcome.
We will always represent step signal u of t with amplitude 1. Is it constant or it will change?
See, a step signal by definition has a constant amplitude after t equal to 0. That is why it is called a step, isn't it? So, it remains constant for t greater than 0.
Thank you, sir.
Alright, so any other questions from your center? No?
Yes, sir.
Okay, thank you very much.
Yes,
now, let us go to Geetham University. So, I am very happy to see there are some students there waiting to ask questions. Yes?
Good evening, sir.
Good evening.
Sir, I am Srikar from Geetham University.
Yes, Srikar.
Can you explain about the time integration property of Fourier transforms?
Okay, very good. So, time integration property. Now, again we will see the same thing by using a single sine wave. So, let us take a single sine wave. Let us integrate this. Let us take the indefinite integral first. So, what does the indefinite integral give you? It gives you a sine omega t plus phi divided by omega, isn't it? So, what has that done? That has caused a phase change of minus pi by 2. And an amplitude change of 1 by omega. And a phase change. So, this is in general true. For all frequencies it does the same thing. So, the amplitude changes reciprocal to the frequency, and the phase changes by minus pi by 2 on the positive side of frequency and by plus pi by 2 on the negative side of frequency. This is what an integrator does in the Fourier domain. Is that clear?
Yes, sir. Sir, can you explain about singularity function also?
Singularity functions. Okay. See, singularity functions are not really functions. So, for example, if you look at the impulse, it is an example of a singularity function. It is not really a function. There is a, see, at the point 0, there is singular behavior. Singular behavior means that the behavior is different from what a function would do. There is something peculiar about that point. So suppose you have an impulse located at a particular point, you multiply a continuous function by an impulse located at a particular point. The impulse is a singularity at the point where it occurs, and when you multiply at that point, what does the impulse do? It picks up the value of the continuous function at the point where it occurs and throws out everything else. You see, so a singularity function is not really a function. A singularity is like a black hole. It sucks up everything at that point and then cleans up everything else. You see, now you can have other singularity functions. For example, you can have the derivative of an impulse, that is the next singularity, and you can keep having higher order singularities. This is a short answer to your question.
Thank you.
Good evening, sir.
Good evening.
So I have a small doubt.
Yes, go on.
What conditions must be satisfied for Fourier series to exist?
What conditions must be satisfied for a Fourier series to exist? Essentially 3 conditions.
Yeah.
You see, one thing is that how many maxima and minima can you have in one interval in a Fourier series? You must have a finite number of maxima and minima in a finite interval. That is one important thing. Secondly, no matter what you do, a Fourier series cannot see. So there is also how many discontinuities can you have? Just as you talk about maxima and minima. Even if the function is absolutely, so if it's absolutely continuous, there is a problem of maxima and minima. Now the next issue is, suppose the function is discontinuous, you can still represent with a Fourier series. But as you know, the Fourier series has trouble at the discontinuities. So how many discontinuities can you have in a finite interval? Only finite. That is also the next. And the function must be a bounded variation. So there must be, so you see, that does not mean the function cannot diverge at all. But if it does, there is a problem. See, for example, so the simple thing to understand is if the function is of bounded variation, that means the function is bounded by a positive number in its magnitude, and that is one of the requirements. Okay? If it is not, then you have to worry about something else. For example, you can have a train of impulses, and you can in principle calculate a Fourier series for that. But there are issues with that Fourier series. The convergence becomes, so bounded variation, finite number of maxima and minima in a given interval, and a finite number of discontinuities in a given interval. These are called the Dirichlet conditions. Okay.
Thank you, sir.
Any other questions from your center?
No, sir.
Okay, thank you. We will now go on to FET in Modi Institute of Technology. There are questions from there. So very good afternoon to FET Institute. I can see there are several students there.
Sir, good afternoon.
Good afternoon.
Sir, I have a question.
Yes,
so the question is, sir, if a signal does not satisfy the Dirichlet's condition, then is it possible to find its Fourier transform, and if it is, then how?
So if a signal does not satisfy the Dirichlet conditions, the Fourier transform will not, see the inverse Fourier transform will not, you might be able to calculate the integral at specific points, but the Fourier transform will not exist in general, and anyway it cannot be inverted. No, so there is no point. Unless the Dirichlet conditions are satisfied, you cannot use the Fourier transform concept in the context of such a signal, because that integral will not really converge for all frequencies, the Fourier integral.
Sir, example of step signals.
Yeah. So in the step signal, see the step signal does not disobey the Dirichlet conditions. The step signal has only one discontinuity.
Thank you, sir. So I have one more question.
Yes.
Good afternoon, sir.
Good afternoon.
So my question is that we are very well familiar with the real signals, for example, the audio and video signals.
Yes.
But sir, how do we visualize a complex signal in real life?
So, you know, in real life, you don't really have complex signals. What you have in real life is only real signals. But then, you know, you can think of complex signals whose real part is the real signal you are dealing with. So, for example, you have a sine wave. If your power supply is very good, then you should get a sine wave at the power supply of 50 hertz. Now, you think of that sine wave as the real part of a complex signal, and then you deal with the complex signal to understand what the power supply does. So, the complex signal is created in your mind whose real part is the real signal you are dealing with. Okay, and you do that because it makes it easier for you to understand the behavior of the complex signal when it goes through certain systems. So, you go to the complex domain, work in the complex domain, and then come back to the real domain. So, in real life you have only real signals, but you can use complex signals on paper to make it easier to understand how real signals behave when they go through certain systems. Is that clear?
Yes sir, thank you sir. Yes sir, thank you.
Yeah. Next question.
So that's it. Yeah,
that's it sir, thank you.
Thank you so much. So, now we have some questions from NMIMS MST Shirpur, Dure. So, very good afternoon. I can see there are several students there. A very good afternoon to all of you.
Good afternoon, sir.
Good afternoon.
So my question is that we study convolution in signal systems, no?
Yes.
So is there any practical application of the convolution integrals in some?
Certainly.
In practical?
Yes, definitely. See, let me give you an example. Suppose I have, suppose I take a simple RC circuit. Capacitive touch. So, you have a simple resistive capacitive circuit. Now, you see the resistive capacitive circuit can occur in many ways. It can also occur as a part of a system. Now, how do you find the response of this circuit to a step? Very easy, you know the response, isn't it? So, if you give a unit step to this, if you suddenly switch on a DC supply here, the output looks like this. And you can find out the impulse response also. So, if I take the derivative, I would get a unit impulse. So, I could find the impulse response of this. The impulse response of this will look like 1 by tau e raised to the power minus t by tau ut, where tau is equal to RC. So, it looks like this. Now, suppose I do not give a unit step to this RC circuit, I give any other arbitrary inputs. You know, I might give a small little ramp and leave it, or I might give some step for some time and change the step at some other time, and then, so you know, I might give many different kinds of input to this RC circuit, and I want to find out the output. Now, every time for every different input, if I have to start solving the differential equation, it is going to be a big headache, isn't it? I give a ramp, again I have to solve a different differential equation, I give some kind of a so if I have to start solving that differential equation of the RC circuit for every different input, such a headache. Instead, I can find the output for all these cases by convolving this impulse response with the input that I give. So, same principle can be applied. Yeah, so if I have a ramp, I convolve that ramp with this impulse response. If I have 2 steps, then I convolve 2 steps with that impulse response. So, it is very convenient when I know how to characterize if a system is linear and shift invariant, like this RC circuit. It is linear and its behavior does not change in time. Then I can characterize it by its impulse response, and once I characterize it by its impulse response, then I can find the output to any input. I do not have to keep solving the whole differential equation every time. Is that clear to you?
Yes, sir, exactly. Thank you, sir.
Yeah, so let us have the next question from your center.
So that's it. That's it.
Okay, very good, thank you. Now I have a question from College of Engineering, Pune. Oh, very good. Welcome to all the students from College of Engineering, Pune. I can see several students have assembled. So welcome to all of you.
Good evening, sir.
Good evening.
Sir, am I audible?
Yes, you are.
Sir, I have two questions.
Yes.
Sir, please explain in detail the concept of energy and power signal. And question number 2 is how to find the energy or power of the functions like e to the power k by t, where k is constant.
Okay, very good. So first, energy and power signals. See, an energy signal is a signal whose energy is finite. So, take for example the signal that you gave me, you gave me the signal e raised to the power minus kt for t greater than or equal to 0, I am assuming, and 0 for less than 0. Now let us try and calculate its energy. So the energy is this. Now this is going to converge only if mod, so k must have, of course we will assume k is real. This will converge only if k is greater than 0. And what will it converge to? It will be e raised to the power minus 2 kt dt integrated from 0 to infinity, which is very easy to integrate. It is simply e raised to the power minus 2 kt by minus 2k integrated from 0 to infinity, which is 1 by 2k. So this is the energy in the signal, it is finite. If k is less than 0, of course this is divergent. This will not be, it will be neither a finite energy signal nor a finite power signal. What is a power signal? A power signal is one which has a finite average power. But if it has a finite average power, it can't have finite energy, because the power would diverge, the energy would diverge. The energy per unit time on an average is finite. But for example, take a periodic function which has finite power. In one period, if the integral of the periodic, if the square integral of the periodic function is convergent in one period, you say it is a power signal because it has finite power, finite amount of energy per unit time. But then it is not an energy signal, because in that case the energy would diverge. Is that clear? Have I answered your question?
Yes.
So next question from COEP. I see several students are sitting there. So welcome to all of you.
Sir?
Yes, good afternoon.
Good evening, sir.
Yeah, good evening.
Sir, while calculating the convergence sum for discrete signal, can you explain how to take the range for the summation when there are infinite signal?
Okay.
Infinite length signal.
Yeah. So see, in general, when you have a convolution sum, so in general, if you have a sequence x to be convolved with sequence h, x goes from n1 to n2 and h goes from n3 to n4. Alright, then x convolved with h would go from n1 plus n3 to n2 plus n4. Alright. So, in general, if you have a two finite length sequences, then you can calculate the range of the convolution very easily. Even if it is infinite, one of these could be infinite. So, for example, n2 might be plus infinity and n4 might be finite, and both n1 and n3 can be 0. This principle will still hold. So, that can enable you to calculate the range. Is that right? Is that clear?
Can you repeat please?
Yeah, could you understand? So, what I said was,
Sir, actually, yes, sir. Actually, I wanted to ask that if when we are calculating convolution sum, how to take the range for the summation, whatever we do the summation of x of k, h of n minus k, for that while taking the range of the summation.
Yes,
and if there are signals like u of n and u of n minus 3 and u of n plus 3, so how to take the range?
Okay, yeah. So let us take. So let me take the example which you have in mind. Can you repeat your example? U of n minus what is it?
X of n is equal to u of n minus 3.
X of n is equal to u of
n minus 3.
N minus 3, and then
H of n is equal to u of n plus 3.
U of n plus 3. Now let us take an example. So let us calculate the convolution. X convolved with h evaluated at n is going to be summation. Now in principle summation over all k. Let us see first. X of k, h of n minus k. But what is x of k? X of k is u of k minus 3, okay, and what is h of n minus k? It is u of n minus k plus 3. Now, in which range are these going to be non-zero? Let us write each of them down separately. So, this one is equal to 1 only for k minus 3 greater than equal to 0. That means k greater than equal to 3. This one is going to be non-zero only for n minus k plus 3 greater than equal to 0, which means k less than equal, sorry, it's okay, we will write it here. So, that means k, okay, write it here, k less than equal to n plus 3. Oh, sorry. Oh, pen. Close this. No, pen, no? What is the you want to activate a pen. So, k less than equal to n plus 3. Alright, so what is the situation? You have this situation, k greater than equal to 3 and k less than equal to n plus 3. So, the range of summation is from 3 to n plus 3. Now, obviously, n plus 3 must be more than or equal to 3, otherwise this summation has no meaning. That also tells you a range for n. Okay? Is that clear how you get the range?
Thank you, sir.
So, next question from COEP.
Okay, that's all. Thank you, sir.
All right. Any other questions? No? All right. Yeah, all right.
Thank you, sir.
Thank you. Now, there is a question from FET Modi Institute of Technology.
Sir,
Yes.
good evening, sir.
Good evening.
Sir, we wanted to know about the pattern of midterm 1. Sir, is it similar to quizzes or different?
Well, you will find out in after a week, but it will be based on what you are studying. So, don't. So after a week, you will know what the pattern is like.
Okay, thank you, sir. Yeah, so that's it. We wanted to know about the midterm 1 only.
All right. Any other center which has questions now? Let's take VIT University, Vellore.
No, sir.
All right. No video. All right. So, can the centers raise their hands if they have any questions? Yashwantrao College. Yes, there is a question from Yashwantrao College. Yes, go on. Your mic is not on. Your mic is not on.
Good evening, sir.
Good evening.
What do we actually mean by energy and power of a signal?
Okay. What do you mean by energy and power? See, energy is the integral of the magnitude squared. Why is it called the energy? If that were to be a voltage going across a 1 ohm resistance, that would be the energy consumed by the resistance, right? So, you have a signal applied as a voltage across a resistance of 1 ohm, the energy consumed by that resistance is the energy of that signal, all right. The word energy or power would depend on the nature of the signal. If the signal is periodic, for example, then its average energy per unit time is constant, but the energy itself is infinite, the energy diverges. See, the energy is not finite, but the average energy per unit time is constant. Okay. So, then you would talk about a power associated with the signal, not an energy. So, the word energy or power would depend on what kind of signal you are dealing with. If a signal is a power signal, then its energy has to diverge, it is infinite. If a signal is an energy signal, its power would go towards 0, its average power would go towards 0. Is that correct? All right.
Yes.
Sir, periodic signal is always a power signal. Having a energy having 0. If the signal having sin t into e of t, it is 0 for minus infinity to 0, and sinusoidally it is periodic for 0 to infinity. So it is power signal or energy signal, sir?
Very good question. So, see, that is an example of a signal which is neither an energy signal nor a power signal. But when you see in asymptotically, it is a power signal. Asymptotically. Asymptotically means what? As you go towards t tending to plus infinity, it is a power signal. As you go towards t tending to minus infinity, it has 0 power. So, it is neither an energy nor a power signal in the strict sense, because the average power per unit, average energy per unit time is not really, it is different for the negative part of t and for the positive part of t, all right. Now, it is definitely not an energy signal, because the energy in that signal is not finite, right. It is not even a power signal strictly, because if you take the average power on the negative side of t and on the positive side of t, they are different, all right. I mean, if you take the average power as t tends to minus infinity, it goes to 0. If you take the average power as t tends to plus infinity, it is finite. So, these are examples of signals where you cannot talk in terms of energy or power. So, you can't, you see, all signals cannot be described in terms of energy or power.
So one more question.
Yes.
So we say that e raised to power at is a non-periodic, but we say that e raised to power j at is a periodic signal by the use of this Euler's theorem as e power j at is equals to cos at plus j sin at. But
Yes.
if we are not using Euler's theorem, and we can simply say that e power j at is equals to e power j into e power at, then how this something a constant e power j multiplied to a non-periodic signal e power at is becomes periodic.
Okay. See, e raised the power, yeah. E raised the power j times at is not equal to e raised the power j into e raised the power at. No, this is not correct. However, you can certainly say that e raised the power j at is e raised the power is cos, as you said, cos at plus j times sin at by the use of Euler's theorem, and both of these are periodic. So, the real and imaginary parts are periodic with period 2 pi by a. All right. Now, what is important is that e raised the power j at for real a, if you add pi or rather 2 pi to the argument, yeah, so e raised the power j at, isn't it? Now, it is definitely equal to e raised the power j at plus 2 pi times a multiple, I mean a multiple of 2 pi. So, this is where the periodicity comes from. Because you can write this as e raised the power j a into t plus 2 pi by a times k. So, adding any multiple of 2 pi by a to t will leave the signal unchanged, and therefore, the signal becomes periodic. All right, is that clear?
So what you have shown up till now, so by that thing it is clear, but I still not satisfied with it.
Yeah, so can you tell me what is it that is causing trouble in understanding?
So the thing is that in the e power at, so the j imaginary term is not there, so it is non-periodic. But in e power j at, that imaginary j term is there, so it becomes periodic by the use of Euler's theorem.
Right. See, the Euler's theorem can also be, you can actually apply the Euler's theorem even for the real case. I will show you. So, if you really want to apply the Euler's theorem, you can do it for the real case. The only problem is then you have to define cosine of an imaginary quantity. So, you can write e raised the power at as e raised the power j times minus j a times t. Is that right? And you can write this as cos minus JA t plus J sine minus JA times t. So now you have to define the cosine and sine of an imaginary quantity, which you can do. So you can define cos of Jx, it's equal to e raised to the power j times Jx plus e raised to the power minus j times Jx divided by 2. So in fact it essentially becomes cosh, it's cosh of x, cos hyperbolic of x, and similarly you can work out for sine. So the Euler's theorem can in principle be used also for the case of a real argument, but it's a roundabout way of coming to that conclusion. So if you are asking me that why the Euler's theorem, you can use the Euler's theorem, there is no problem. The only difficulty is that Euler's theorem is not very it's not going to give you any new insights in the context of a real argument in the exponential. Okay, so that is the first part of the answer. The second part is, see, the Euler's theorem is a very powerful idea if you think about it. See, what it tells you is that you can raise e to a complex argument in general, and the way you deal with a complex argument in the exponent is you split it into a real part and imaginary part. The real part has to be dealt with as usual when we deal with e raised to the power a real quantity, that is not a problem. The imaginary part has to be dealt with by using the Euler's principle. So actually the Euler's theorem is essentially a mechanism for extending the definition of e raised to the power of x to complex x, right? And here in one case you are taking only a real part, and in the second case you are taking only an imaginary part, and naturally the two things are very different. Is that clear to you?
Yes, sir. Thank you, sir.
Okay, thank you. So it's nice that you stayed back and asked these questions. Right. Okay. So any other centers have any questions now? Okay. So I think we can now conclude this interaction session.